Okay, so good morning. This morning session highlights the development, application, and reduction of gas and particle phase chemical mechanisms for aerosol predictions. So S2A formation proceeds by reaction with volatile organic compounds in the gas or particle phase, and efforts have been made to better understand the different chemical pathways leading to S2A formation, their impact on concentrations, and the evolution in future air quality. So this morning we will see methodology to reduce complex S2A chemical schemes, as well as examples of aerosol properties that are often not modeled but important for S2A formation. So our first speaker is Zhizhao Wang. She obtained her PhD in environmental science and technology from École des Ponts in France this year, and her research focuses on the development and application of mechanism reduction algorithms that generate condensed S2A mechanisms from explicit DOT chemical mechanisms. And she's now a postdoc at NCAR.
Thank you for the introduction. Hello everyone, my name is Zhang, and I'm happy to be here today sharing with you my work on the topic investigating anthropogenic emission mitigation effects on biogenic SOA formation using different SOA mechanisms. So I'll begin with some background information. So volatile organic compounds we will see can undergo gas-phase chemistry. Their oxidation products with low volatility can be condensed and form secondary organic aerosol SOA. Anthropogenic emissions can influence this process, especially NOx, nitrogen oxide. They themselves are not only important pollutants, and they can also participate in the formation of many secondary pollutants, such as showing here the formation of ozone and orange radicals, for example. So if we take a closer look at the VOC chemistry related to SO formation, we can see that VOC can react with atmospheric oxidants and form peroxide radical RO2. Those RO2 can undergo oxidation or RO2 reactions with NO, H2 or another RO2 form solenoid organic compounds as VOC. So we see that here NOx and NO can directly react with RO2. Also, they participate in the formation of oxidants, which means the effects of anthropogenic emissions on SOA formation is very complex and non-linear. So how can we simulate accurate SOA response of anthropogenic emission mitigation based on those knowledge? So currently, SOA formation is simulated with mechanism built from bottom-up approach, where blunt mechanism associated with a few model species has been applied to simulate the entire SOA formation. So here, this is a general equations. We can see that the model species can be volatility means or surrogate approach. So it's quite straightforward, but it's quite simple. So there may not contain enough information from VOC chemistry on SOA formation. On the other hand, we have protocols that have been developed to generate detailed VOC degradation scheme from target SOA precursors. With that top-down approach, we can build mechanism with multi-generation reactions and numerous organic species. So which means there will be enough information related to SOA formation. However, due to their large size, it's overwhelming to apply them directly in 3D simulations. So therefore, mechanism reduction algorithm is required to apply those information that we have from top-down approach to current 3D simulations. So that's where GENOA comes in. So GENOA stands for Generator of Reduced Organic Aerosol Mechanism. It contains 3 main processes: initialization, training, and testing. So the reductions is happening in the training process, where a set of critical named reduction strategy all kind of things are kind of mixed together, but we don't really put into the utility. So the most time consuming part actually is a complete gas particle partitioning, because you're gonna distribute all the like the computing partitioning and distribute the different side beams, which is take a lot of time. So that's what we first developed to really kind of focus on aspect to reduce the number of participants, which like consume a lot of time in dirty, which means of course we switch. So yes, that's the first effort. Yeah.
That's interesting. We have an opposite problem in the CRCT and partitioning took like less than 1% of the wall time, and infection was most of it, affecting those away traces. So interesting. We can talk more plan.
Great. So the next speaker in this session is Haofei Zhang. He's an associate professor in chemistry at UC Riverside. His research is on atmospheric oxidation of VOCs, SOA formation, and chemical evolution of organic aerosols. His primary research techniques are mass spectrometry and kinetic modeling. And today he's going to talk about an Isoprene SOA kinetic model.
Good morning, and thank you for the invitation and introduction. Today I'll be presenting our recent work done in my group on model development, mechanism reduction, and also evaluation against laboratory experiments and field measurements for isoprene secondary aerosol. So first, I'd like to acknowledge my postdoc Chen Yang and graduate students and for doing most of the work, and also collaborators for their contributions, and lastly, Vanessa for funding support. All right, so the motivation to study isoprene SOA is quite obvious. This little 5-carbon molecule is largely emitted from biogenic emissions, and it's actually the largest non-mixing VOC emitted into the atmosphere, reaching about 500 to 600 teragram per year. And despite the very low SOA yield, because of the large emission, isoprene is still predicted to be the dominant contributor to secondary organic aerosol in the atmosphere, especially in the regions where biogenic emissions or isoprene emissions are high, such as the forest, Africa, Australia, and southeastern United States. All right, so I pretty much presented the same introductory slide and I did my PhD defense about 10 years ago. So it's kind of cheating, especially after I moved away from isoprene after that. But the question today is, why are we still interested in isoprene? Right? In the past 2 decades or so, there have been many studies published on isoprene chemistry, including the isoprene gas phase reaction pathways, secondary organic aerosol formation, molecular level composition from laboratory studies, supported by field observations. But to sustain this well-known three legs stool for chemistry, it's very important to connect these two aspects to atmospheric modeling. And we think because isoprene chemistry is sort of relatively well-known in comparison to many other VOCs emitted into the atmosphere, and we believe isoprene can be a very good candidate to allow us to build a connection. All right, so to do that, first, we need to have a reasonable chemical mechanism to represent isoprene oxidation, and then we need to reduce it to a size that's usable by atmospheric models. All right, so first, let's take a look at the general isoprene formation pathways. Right, so there are 2 major generic pathways leading to SOA formation from isoprene oxidation. The first one is through the formation of different oxides from isoprene oxidation. For example, this isoprene the IPOS from the low NOx pathway and HMML and A from high NOx pathway. So those epoxides can undergo reactive uptake processes, especially when the aerosol particles are liquid and or containing acidic sulfates. And the other generic pathway is from forming multifunctional products that contain at least, say, 4 functional groups. And so those products have low volatility and then can undergo the traditional alternative gas particle partitioning form sector organic aerosols. Right? For species we'll talk a little bit more on, we'll consider those that without nitrogen given the C5 low volatility after Equinate, and those containing nitrate or nitrogen C5 and LV. Right, so this is a kind of a very general theme for isoprene formation. And then moving on to talk about isoprene modeling in box models and chemistry models. Right, there are 2 general methods. The first one is using the highly simplified volatile business set based on laboratory experiments on volatility of products, and we use different volatility beams to represent the gas information. It's very highly simplified, and there's parameterization based on chamber experiments. But the problem is that under different conditions in chamber experiments, these parameters might be different. And also, there's no molecular information retained from the VPS kind of approach, so that if you want to understand what are the composition of the predicted SOA, you don't really have that. And the other extreme is that you represent the chemistry with highly explicit or near explicit mechanism, and you represent as much as possible that we understand and to simulate SOA. In this approach, you have very detailed molecular information, but usually it's too large to implement into abstract models. And also sometimes the atomic level details are not necessary and sometimes not accurate. So what we need is something in the middle that we can represent the key molecular information and small enough to equally reflect different models, and also retaining the useful informations, right? So that's our goal for this work. So this is what people typically have in their isoprene mechanism. That includes the key isotope precursors, isotope IEPOS, which undergo reactive uptake processes, and also from the inox, there are also processes forming SOA. Right, so in our multiphase isoprene mechanism, we included a few more pathways, including the under low NOx, the isotope and IEPOS, also undergo further oxidation by OH to form these low volatility products. And also under inox, this isoprene hydroxynitrate also oxides to form these natural containing species. And also we include nighttime chemistry for isoprene, but I don't have time to talk about that in more detail. But in general, we have this mechanism, and we use the framework for zero-dimension additive modeling, the full framework to model. And a few key features. So the gas-based mechanism is built on top of Cycle 7, which is already being used for rigid models like the CMAC. Right, so we added about 59 species and 118 reactions, so it's already reduced. Then we reduce it based on the Caltech, MCM, and FCJ mechanisms. So we advance further based on those mechanisms to represent the most updated information. And then the oxides and the reactive uptake processes in the presence of this phase or acidic sulfate. And then we include low volatility products undergoing the gas particle partitioning. And lastly, we consider particle-based hydrolysis for hydroxides and also hydrolysis for nitrates. So those were based on existing. All right, so then some evaluation of the model. Right, so let's look at gases mechanism first. So these are 3 experiments done at the UNC Chapel. So those are inox experiments. So we have isoprene ozone and NOx evolution, and then comparing with the other values, the when we use the mechanisms, it's a new UCR model is performing a reasonable prediction for the actual brain ozone and numbers. And then these are the 3 experiments that we have also evaluated, like 30 experiments, and compared with the other mechanisms. The mechanism is reasonable in terms of these simple gaseous equations. Right? But we're not only interested in ozone numbers, we're interested in organics and SOA precursors and SOA species themselves. Right, so then we continue to compare our mechanism with the other mechanisms, especially because for a lot of the organic species, there's no quantified measurements, so there's no way to directly compare with observations. So the way we do it is we compare with the Caltech mechanism simulations using our mechanism and the NCAR for a lot of the gaseous species to make sure when you use the mechanism, we're not sacrificing the accuracy of the mechanism. Right, so this is for MECR and UK, and this seems we do a reasonable job spending 2 or 3 orders of magnitude of concentrations. Right, and we did a similar comparison with other gaseous species, for those that have audience. Now we are gaseous species without provision. Right, so we were doing a really good job in terms of comparing with the challenge. All right, then moving on to the SOA simulation. So this is a comparison between measured SOA concentration and model SOA concentration using our mechanism against experiments done at Caltech and also Emission meters. Right, so these are not representative part of this real time series experiments. And the low down condition, I think our model is doing reasonably well with the plus minus about 50% in terms of SOA concentrations, but in the high loss condition is a more complex situation. Even the initial recipe ratio is low enough to say below around 2, we're doing kind of similar performance, similar to the low loss situation. So the recipe, low recipe ratio is very high, rather than 2. It looks like the chamber experiment observed a lot of SOA and we're not able to predict any SOA. And that's not because of the reduction of our mechanism. The same goes for the Caltech mechanism and NCAR mechanism. So it looks like there's some basic understanding of the processes for high loss species. But this is probably not a big deal when we continue to simulate ambient environments under low loss environment like SOAS or something like that. Right, so then evaluate our mechanism with the SOAS field measurement. It's field campaign, the solvent oxygen and aerosol study back in 2013. Right, so that's the picture of the site, and this is where the site is located, where we have really high emissions. All right, so the very good thing about SOAS is it was a highly instrumented campaign, so there are a lot of measurements. So we use these real measurements to constrain our model, so like Isoprene, OH, NOx, ozone. So those measurements we use to constrain our inputs into the whole model. And some additional considerations, we also consider dry and wet deposition, dilution, decreased phase uptake, and aerosol phase state based on the weight. So we consider those issues that we didn't have to for evaluate chamber experiments. All right, so this again is comparison. We're trying to use tune the dilution rate to have a reasonable simulation, real-time simulation with MECR plus MEK. We are supposed to have we have a good understanding of their formation pathways from measurement, and we're doing a okay job reproducing MECR. But when we move on to Isoprene and multiphase and IAMA and Kinetic, we're predicting their concentrations. And by the way, this is already after we consider the reactivity of these species. So we think there's some missing since for these species in the gas phase that we're not really considered part of the image. Right, but if you look at comparison between the C5 LV and C5 LV between UCR and Caltech mechanisms, they're almost identical. Just when we reduce the mechanism from the Caltech mechanism to our mechanism, where we didn't lose any accuracy in terms of these species. And these are really the key species in terms of predicting X-ray formation. So then let's look at the X-ray comparison. So we're comparing our models and we rate this measurements buffers. So the error bar represents the quartiles, the median during the campaign. And it looks like we're doing a decent job reproducing the times time trend, diagonal trend of the CMAC LP measurements. And those are dominant species that our model represent low-NOx formation pathway. And then for the high-NOx pathway, we're predicting by 1. And that's partly because the measurements have high absolutes. So those were species were calibrated based on the nitrate, which they have lower sensitivities compared to some of the other than the light species. But we're overall having 2 or 3 species on the high-NOx isolated composition. And then moving back to this mechanism I showed earlier, so these are the key species from the low-NOx pathway, and these are the key species from the high-NOx pathway that contribute most to the actually predicted surface. All right, and then moving on to talk about the traditional epoxide uptake pathway. So here we predict the epox uptake, including the epox derived again sulfate and cemented. And by comparing with the measurements, I think we're doing reasonably well. There are no variation as well as the magnitude. And then if we stack all of these together, and we look, it looks like the non-epox secondary aerosol can account for a little bit more than 50% of the total Western gas. So it's a little surprising and unexpected, but it's a little higher than epox responsiveness. All right. And to wrap up my talk, so we're developing new gas mechanism based on the recent Caltech mechanism and MCM and the Zhizhao mechanism. We have a pretty good consistency with chamber experiments, and we're not doing over extreme to further reduce the mechanism and make it more applicable to large scale regional models like SNAC. And the low voltage pathways with a large fraction, the field has X-ray formation 57%. And lastly, we think further studies are needed on specific conditions, for example, the high-NOx conditions that needs to be done to better understand the X-ray pathway and X-ray. And with that, I would like to thank you for your attention and like to ask questions.
For people that think about their questions and maybe have some comment on Slido, you showed a comparison with SOAS field campaign, and you talked about not having sufficient sinks. But I guess I'm wondering how you're sure it's not overproduction of like Isoprene. So, like, there we go. Yeah, 13. So here for like your IH and your Isoprene, like in the model, you don't think you have sufficient things, but I guess I'm curious why you're sure it's not overproduction.
Right. So for Isoprene, iPods, and the hydroxy nitrate, so they were first generation products. And there have been a lot of studies done, especially in Caltech, that did very careful actually involve evidence in the lab. Yeah, it's information.
Just leave it for the moment till I get that up.
I don't think those Kinetic informations are very accurate. Right. So one possible limitation might be the quantification through the field, because field campaign might have some possibilities. But I think the mechanistic understanding of this formation are probably accurate enough to lower differences. So maybe there are like infections files that were not considered.
It relies on accurately.
Right. Yeah, so we anticipate based on that. So whatever options are either missing these individual parameters.
Other questions? Mary?
Thanks, Mary Barth from NCAR. So with the same slide, maybe I wasn't paying attention very well, but how did you control the meteorology to come up with this chemistry time series?
Okay, so
Right, because
meteorology-
again, going to maybe effects of clouds or different air masses.
Right, so meteorology, we use real-time measurements of the temperature, relative humidity, on the river constraint, temperature. So for 0D models, the limitation is can actually represent the connection. So we use a single parameter dilution. But we use the dilution, we manually tune the dilution rate to make NCAR decay measurements and models, make them consistent. So that's the kind of dilution rate. So we use that to hopefully recapture those conditions.
Yeah, so that makes sense. I would be curious if there is an effect of clouds, because I know some of these last cases had like fairweather cumulus clouds that we talked about. The larger they seem like larger these in the weather could bring down a different concentration. But very interesting.
Okay, more questions?
I have a quick question. Did you include IHN hydrolysis in the mechanism? Because I don't think that's included in the original count.
Yes, okay, you do that. You know that, like, the one PI customers, they will grab it.
Yep.
Great.
Next presentation is from Hodzic and Camille. So it's online, so online virtuals, right? So Camille Mouchel-Vallon recently joined the Barcelona Supercomputing Center, and he did a postdoc at NCAR, Anthropogenic, and at the Laboratoire d'Emulation in France. And he will give us an overview of ongoing efforts on machine learning-based emulation of this information.
So good morning, everyone. I'm Camille Mouchel-Vallon, and I will be presenting on behalf of Alma Hodzic. And I will be showing you work we have been doing in the last few years about emulating secondary organic aerosol formation with machine learning tools. Of course, this work was done with the help of other people, so colleagues from NCAR and also CU Boulder. I will start with quickly introducing the challenge in representing organic aerosol chemistry in 3D models and how we try to solve them with machine learning. And I will show you some of the results we have been able to obtain and quickly conclude after that. And the challenge we have in representing organic aerosol chemistry comes from the fact that the volatile organic compounds are emitting from various sources, human, biogenic, or from biomass burning. And these compounds, they are transported and evolve in the atmosphere. And if they have a low volatility, they will condense to form organic aerosol. And the properties of this organic aerosol will determine their direct or indirect radiative forcing, as well as their impact on air quality. The problem is that, as the speakers before me have said, that is this organic chemistry involves a lot of chemical species. So I wrote here more than 10,000, but if you ask me to add 2 or 3 zeros, I wouldn't be mad. And the issue comes from describing this detailed chemistry. For instance, if you look at this this visualization of the MCM chemical mechanism that was shown in this Lewis paper, you see here each dot here is a distinct distinct chemical compound. And the lines between each dot is the flux between each of these compounds. So it's basically one chemical reaction. And you can see the complexity arising from this chemistry and how it could be difficult to represent in a model.
Yeah.
Sorry, you're saying something? The complexity of this organic chemistry can be treated in box model, and what we want to represent is basically the multi-generational addition of oxygenated function of the carbon on the carbon skeleton, because these are these organic functions that will determine the properties of the molecules in the aerosol, in the secondary organic aerosol. And to represent this progressive oxidation of organic compounds, there is this tool called GECOA that was developed in LISA in Paris and NCAR, the generator of explicit chemistry and kinetics of organics in the atmosphere, and it is used to generate very detailed chemical mechanisms. Of course, because we want to represent all the details of this chemistry, the resulting chemical mechanisms are extremely big. As an example, the oxidation of alpha-pinene could represent more than 2 million reactions involving hundreds of thousands compounds. So obviously, no 3D model is able to run this. So the chemistry climate models, for instance, we rely on simplistic empirical organic aerosol parameterization, but this empirical parameterization do not allow us to know the detailed properties of the organic aerosol. So to try to see if we could bring the organic complexity to the 3D model, we were inspired by an approach that was described by Keller and Evans in a paper from 2019, where they tried to emulate the chemical mechanism that is present in the GEOS-CAMP global model. Basically, here on the left are the traditional processes represented in a numerical 3D model, with the chemical integration step being one of the most expensive one in the model. And what they did is that they basically intercepted the state vector before chemical integration and after chemical integration, and used that as training data to train machine, in their case, random forests. And the idea is to train a random forest that is able to emulate the behavior of the chemical integrator itself. The idea being that if it works like the chemical integrator, but has a much lower computational footprint, we would save a lot of computational time. And the idea here is that we try to follow a similar approach, except that instead of using the chemical integrator from GEOS-CAMP, we want to emulate the behavior of GECOA, so of very detailed explicit chemistry. For that, we tried two different approaches in two different papers that I will introduce next. So first, we use neural networks, and then we also used random forests. The neural networks that we used were first the traditional multi-layer perceptron model with 3 layers, an input layer, a hidden layer, and an output layer. The input layer involves inputs related to the environment, like temperature, solar density angle, and also the chemical environment, like the OH content or ozone or NOx concentrations. And we are predicting, in that case, the precursor concentration, the secondary organic gases concentration, and the secondary organic aerosol concentration. And the addition is that because we want to have a time evolving model, these outputs will be used as inputs for the next time step. In addition, this multi-layer perceptron model was augmented with a gated recurrent unit. So I'm not a specialist of that, but I try to explain quickly what it does. Basically, the GRU adds a hidden state, and the role of the GRU is to combine the existing input and the hidden state to produce new inputs that are used by the hidden layer, and another new hidden state that will be used again afterwards for the next time step. And the role of the GRU is to behave like a memory of past events in this neural network. So the idea is that it would keep in keep in memory what happened in a few previous time steps. So now that we have the neural networks that we are going to use, the idea, we need to build the training data set that is necessary to train the neural network. In our case, we run GECOA, we ran many simulations with GECO-A to build the training set. And we did that for 3 different precursors, toluene, dodecaine, and alpha-pinene. So it's 3 individual precursors. So we train different neural networks for each precursor. And we initialized all the simulations with different random environmental conditions. And these environmental conditions that are about the environment, meteorological environment or chemical environment, they are all maintained constant for the whole simulation, except temperature that is allowed to vary sinusoidally. And the initial precursor amounts were set at 10 ppt, 100 ppt, or 1 ppb. So a typical training simulation looks like this, where you have in blue the decay of the precursor, in orange the formation of secondary organic gases, and in black the slow formation of organic aerosol in that case. So we ran 2000 random experiments like this one for each precursor with a 5-minute output for 5 days. So it gives us at the end 3 million samples, 3 million time steps to train the neural network. Here is what this training data looks like. If we summarize, each point is the average for a given simulation. On the y-axis, you have the targets that we are trying to predict. So the precursor, the gas concentration, and the organic gas concentration, and the aerosol mass concentration. And on the x-axis, you have different environmental constraints. And the colors depicts the temperature of the average temperature of the simulation. And as you can see, what we illustrate here is mostly the complexity involved in trying to predict aerosol mass, because there is no obvious relationship between the environmental condition and the aerosol mass that we are trying to predict. We can see some obvious things, like if the temperature is increasing, the aerosol mass is decreasing because of evaporation. Or in that case, if OH is increasing, you will have lower concentration of the precursor and higher, vaguely higher organic aerosol mass concentrations. And we can look at the result of the neural network in this framework. Here with the 30 ensemble member prediction, basically it means that for the 30 neural networks were trained on the same training set, except that they are all initialized with different random weights. And in our case, for the basic multi-layer perceptron, you see here the time series of the GECO-A truths in the black line, in the black dashed line, and each line is one of the ensemble member. In each color line is one of the ensemble member, and the thick colored line is the average of the ensemble members. And you can see that after the few hours, the multi-layer perceptron neural network is diverging from the truth. And for instance, in this second simulation, we have more than a factor of 2 of error after less than 20 hours. However, when the gated recurrent unit is added, the behavior is much better. And we can say that the GRU helps keeping the simulation stable for 5 days. Yeah. So the GRU is performing better, but as a reminder, because of the hidden layer, it might be more challenging to implement in a 3D model, for instance. However, when we try to apply this neural net in real diurnal cycle conditions, these are the results that we obtain. So in this case, we run GECO-A simulations with a diurnal cycle. And we initialize this, we try to simulate the same situation with the multi-layer perceptron. And as you can see, the neural network is not able to reproduce these realistic diurnal cycles when it was trained with relatively simplistic simulations dataset. So what it tells us is that we still need to train the neural networks or any machine with a realistic diurnal cycle. If you want to be able to reproduce diurnal cycle, we cannot simplify the training simulations. Yeah. So, oh yeah, here's the computational time break. So because we do all that to accelerate calculations, computation time. So here is a table of the comparison between GECO-A runs and the time it takes to run the emulated version of this mechanism. And as you can see, we gain even for Tolwyn, we gain between a factor of 400 and a factor of 10,000 when running the multi-layer perceptron on GPUs. So I was saying that we switched to random forest for this second part of the presentation. So same approach as the neural network. We have an inputs that are the predictor, the precursor concentration, the gas phase organic concentration, and the organic aerosol concentration, as well as some environmental conditions and some chemical environment. And there are a few other here that I didn't show. And the idea here also to simplify things, because it's kind of not really useful. We are not predicting the precursor concentration. We are just predicting the organics concentration in the gas phase and the aerosol phase. We did our study with only two precursors, toluene and dodecaine. We skipped alpha-pinene because building the training set was very long. And this time we also randomized environmental conditions with ranges that this time were taken from typical 3D model tropospheric range. Basically, we took a 1-year geoscam simulation and we took the range of these values. But this time the box model simulation that are used for training were simulating a diurnal cycle. It means that most of the chemical, all the chemical compounds were allowed to vary with time, and the solar zenith angle was also varying with time, and it depended on the latitude that we prescribed. Temperature and pressure and relative humidity were set at a constant value however. And also the initial precursor conditions were random. And this is what the typical training simulation looked like. So same as before, we have the slow decay of the precursor, formation of organic gas and organic aerosol. And you can see that we here are depicting a diurnal cycle with the daytime oxidation and almost nothing happening at night. So yeah, again, only predicting 2 targets, and this time we have approximately 1 million samples per precursor to use. So here is what we can see for typical simulation, the results of the random forest. So here we have the mass concentration of organic gases and organic aerosol for toluene and dodecaine simulations. The dashed line is the GECO-A reference, and the plain line is the random forest result. And you can see that the random forest performs similarly to what we have seen for the neural networks. And it's able to reproduce diurnal cycles because we trained it on diurnal cycles. And we can have a more general view of the performance of the random forest. Here, I will try to explain this graph as best as I can. So here we have on the left the Pearson correlation coefficient distribution, and on the right, the normalized RMSE distribution. And in gray, we have distribution for when we predict individual time steps independent from each other. And in orange, this is what's interesting to us. It's the full simulation run, the performance on a full simulation run. And you can see here that we have on the x-axis the number of training points that were used to train the random forests. And you can see that increasing the training sample size will improve performances. And but the returns are kind of diminishing because going from 100,000 to 1 million training points doesn't increase the performance that much. So there is a limit to the size of the training sample we could use and have some benefits from that. But we can look at how this error is distributed to see how we can better build the training set. Here, I plotted the different variables as a function of the and the quartile of the root mean square error. So from black to green, we have an increasing error in the random forest. And you can see that for instance, for quantities related to aerosol that we are trying to predict, like the seed concentration or the aerosol mass yield or aerosol mass concentration, the errors are not really sensitive to these values. Well, not a lot. However, they are sensitive to the mean OH concentration, because the error increases for toluene, for instance, when we increase the OH, or to the RO2 regime, that is RO2 reacting with NO mainly or with HO2. And we can see that with a lower NOx regime, for instance, in the toluene case, the error is increased for the lower NOx regimes. And as we saw that it's because these regimes were under all the chemical regimes are properly represented. So a way to look at this is to see if we reduce the range of regime that we are trying to predict, do we improve the performances? So what I did in that case, between low NOx, mid NOx, and high NOx, and train 3 different random forests for each of the precursor and see if we improve performance. And basically what came out of this is that specializing the random forest might be a good idea, but it would require more training data or better constructed training data, because the specialized random forests were not behaving better than the original random forests. Additionally, because with random forests, we were able to try to explain to try to pick the relative importance of each of the predictors. And here I plot the relative importance of each of the predictors used by the random forest for each of the precursor. The number at the top are the ranks. And the importance of the predictor is similar for both species, except for a few that are switched. But what we found from that is that some of these are absolutely not important, like the solar zenith angle of the GENO2. And I believe it's because the information given by the GENO2 or the solar zenith angle is in fact also an information that you can find in the ozone concentration evolution or the NO2 concentration evolution. So what we have here is that predictors that are correlated. And so if you have multiple predictors that are correlated, then you are distributing the predictive power of this variable between the correlated variables. So maybe we are losing some predictive power in the random forests. So what I tried to do is to reduce the number of predictors. So I selected the top 8 predictors for each of the precursors and looked at how the random forest behaves when I reduce the number of predictors. And this is the result here, where I have a diagram of the Pearson correlation coefficient as a function of the normalized RMSE for the original random forest and the random forest where I kept only half of the predictors. And as you can see, the colors showed simulation that improved from one to the other when I switched from to half of the predictors. And we can see that for the worst performing simulations, the performance have improved. So it highlights the importance of selecting predictors and dimensionality reduction that come with it. And finally, to finish, I want to show a small test that was done by the colleagues at CU, where they implemented the Gecko neural network in GeoSChem. So we come back to the neural network because it was the simplest one to implement in GeoSChem, and we compared it to the VBS results on a 1-year simulation with GeoSChem. So here we have the monthly average predicted toluene SOA for May 2016 with the Gecko neural network and the VBS. And as you can see, at least the neural net is able to see the hotspots that the VBS is predicting, but the values are approximately a factor of 2 below what was predicted by the VBS. However, the simulation was stable over several months, which is already quite nice. even if we are in a factor 2 or below, we were a factor 2 away from the VBS parameterization. So to conclude, we saw that it's possible to emulate the behavior of very detailed atmospheric chemistry mechanism with machine learning. We are able to achieve long-term stability in box models for the neural network with the gated recurrent unit. But we highlighted that the training dataset has to be carefully constructed to cover all the environmental conditions that we are going to treat, including diurnal cycles. The random forest are able to perform similarly to the neural net. So that's good. So it means that we can keep exploring different methods and see which one are better. And also the predictor selection is crucial, and we have to work on the dimensionality reduction, maybe automate it instead of doing it by hand to improve our models, our machines. And finally, we are looking, we still need to do a proper 3D model implementation of the random forest. And in the future, we need to predict more than aerosol mass and look at how to predict toxicity, hygroscopicity, or optical properties of the secondary aerosol with machine learning, and for more than one individual precursor. So what happens when we have a mixture of multiple precursors? How do we combine maybe results of different random forests, or how do we train random forests to simulate SOA from from a mixture of different precursors is still an open problem. And these are things that I'm currently looking to work on in Barcelona. And thank you for your attention. I'm sorry for the noise issues. And if you have questions, here are our email addresses.
Yeah, I have a question related to the complexity of what you're not showing. And you're showing the integral quantities, gas and aerosol. But obviously, as a function of time, there's a huge change in complexity and volatility distribution, etc. I just wondered if gas and aerosol could be right for the wrong reasons. And if you start kind of drilling down into what's implied in that, you'll actually find it's just not realistic. But have you looked at anything more than just gas and aerosol?
I'm not sure I caught everything you said. So I haven't looked at more than just gas and aerosol mass at the moment, but I believe that we should start looking at other properties, and we need to think about which properties we need to capture to be able to predict more than just the mass. So whether we want to capture optical properties or hygroscopicity or, I don't know, functionalization, I don't know yet, but we haven't looked at it in details.
So Mission is a PhD student at the University of Illinois in Champaign, and she's in the whole research group. And she's going to talk about seed-dependent chemical growth in using PartMC-CAMP.
Thank you for the introduction. So today I'm going to discuss about seed-dependent particle growth and how we model them through multiphase reactions using our modeling framework, PartMC-CAMP. So my research was motivated by the recent work from Dr. Marie Johnson's group. They found that the growth rate of secondary organic aerosol depends on the composition and phase of seed particles. For example, wet ammonium sulfate seed grow much faster than SOA seed when they are exposed to the product of alpha-pinene osmosis. This is likely due to the chemical processes on ammonium sulfate that transform semi-volatile osmosis products into non-volatile secondary products. And the processes could be, for example, oligomerization or organosulfate formation. So we would like to explore the question that if such process exists, how does that affect size distribution and CCN activity? We approach that in two steps. Step one is to develop a mechanistic model treatment for seed-dependent growth. And step two is to perform population level simulations. Now, for the step one, to develop a mechanistic model, we need to first figure out all possible chemistry involved. And here I'm showing major pathways that contribute to the growth of different seed particles. For SOAC, they are mainly grown by the condensation of NVOC and partly by the partitioning of SVOC. For wet ammonium sulfate seed, except for the two processes, we also have additional chemical process. Things we don't actually know the exact reaction occurring in this particle phase, so we just assume the simplest thing, that is SVOC transformed into NVOC through Arrhenius reaction. For the chemistry part, we use integrated multiphase chemistry model CAMP. And the cool thing about this model is that we can use JSON input file to describe any gas and particle phase chemical mechanisms without need to recompile the model. Here I'm showing two examples. The first one is the partitioning of SVOC into the organic seed. And by adjusting those parameters, we can determine the volatility of that SVOC. I will include more details in the next slide. And the second example is the condensed phase reaction in the inorganic seed. And we determine what are the reactants and the products are. And also by adjusting those parameters, we tell the model how fast we want this reaction to occur. Now, a little bit more details about these parameters. So the parameter set are specific for different reaction type. For this condensation or partitioning process, we use a set of beads to calculate temperature-dependent equilibrium vapor pressure. And those beads were defined by the functional group of organics. And for a condensed phase reaction, we use parameter A, B, C to calculate the Arrhenius reaction rate constant. For the particle part, we use a particle result model, PartMC, and we have a Python version of PartMC, and more details will be coming in the talk this afternoon. So what PartMC does is to treat each particle as discrete computational particles. We store the condensation information as an A-dimensional vector. This allows us to calculate composition-dependent growth rates. Now, back to the experimental results. To quantify the growth rate on different seed particles, they use a parameter called relative growth rate. For wet ammonium sulfate seed, it has a growth factor about 3 times more than SOAC, but we can use this growth factor directly. We need to use a reaction rate to translate that growth factor into our model. How do we do that? First, we need to understand the meaning of growth factor. So the experiment was conducted in a Bluetooth reactor. They measure the difference between outlet diameter and inlet diameter to know how much the particle has grown. And then we assume that there is no condensed phase reaction occur. We pretend that particle only grow by condensation. So growth factor tells us by how much we need to increase the gas concentrations to get that observed particle growth, this delta dP. For example, we know that wet ammonium sulfate seed has a growth factor of 3. So that means if we pretend there's no condensed phase reaction, we need to increase gas concentration by 3 times to get that observed particle diameter. Now, we can perform simulations to mimic the experiment. There are 3 independent simulations. The first one is the baseline simulation. Those were the initial gas concentrations, and we pretend there's no condensed phase reaction. This is mimicking an experimental result having growth factor of 1, and then we increase the concentration of NVOC by a factor of 3, and again pretend there's no condensed phase reaction. So this is This tells us what a particle can grow into if it has a growth factor of 3. And the third one is we have the same growth gas concentration as the baseline simulation, but now we turn on condensation reaction. This tells us what an actual wet ammonium sulfate seed growth should look like. After the 3 independent simulations, we get 3 curves. So for the baseline simulation, the particle increase in diameter the smallest. And for base 3 times case, the particle we get larger particle diameter at each time step. So remind that our goal is to find a reaction rate that can translate the growth factor into our model. So that reaction rate is determined by parameter ABC in CAMP, and we use Python SciPy package to get optimized parameter that we can make this curve as close as to A3x and then converge to. So here I'm showing the optimized parameters. Now with all that done, we can perform population level simulations. We start with a unimodel distribution. Inside this distribution, there are actually 2 identical distributions. One for externally mixed ammonium sulfate and another for externally mixed SOA. They compete for the gases, and we perform 2 independent simulations. One will assume ammonium sulfate and SOA grow the same, and another one we have ammonium sulfate have condensed phase reaction. So you see for the size distribution, it shifts to a larger size. And if we plot the size distribution for ammonium sulfate and SOA separately, it's actually the ammonium sulfate pulling the size distribution to both. And for CCN activity, if we assume there's no condensed phase reaction occurring in ammonium sulfate, then we are actually underestimating the CCN activity. Then we looked at prime model distribution with ammonium sulfate in the small mode. This is more close to a rural area setting where we have new particle formation dominance. And you can imagine because those small ammonium sulfate grow much faster, so they will catch up this large node. And the distance between those 2 nodes are actually reducing. For CCN activity, again, we are underestimating activation ratio if we assume there's no condensed phase reaction inside ammonium sulfate. Then we switch the order of those 2 modes. Now we have a SOA in the small mode. And this is more close to an urban area setting where we have more organic emissions. And because SOA in the small mode, they don't have enhanced growth, and ammonium sulfate is already large, so their growth is also not that significant. So there's no difference in the size distribution for the 2 independent simulations. Therefore, there's no not too much change in CCN. And to summarize, we created a framework for seed-dependent particle growth using PartMC and CAMP. We've translated the growth factor into reaction rate. And we found that the impact on CCN concentration is significant when ultrafine ammonium sulfate seed undergo enhanced growth. In the future, we plan to refine our mechanisms and perform scenario analysis going from simple mixing state to more complex cases. And with that, thank you for your listening, and I'd be happy to take any questions.
Thanks. So I was curious, in your you showed a plot of the growth of your
somebody over there.
3 and then your condensed one, and your base times 3 growth rate only seems to be double your base one, because your base one grew by 10 nanometers-ish, and then your base chemistry grew by 20 nanometers. And maybe some of this is that you're going from the kinetic and transition regime, but I'm surprised that it's only doubles. Yeah, so you go from 40 to 51 in the base, and then you go from 40 to 62 in the base times 3. So I thought you'd be closer to a tripling in growth rate. Double. Do you know why?
Well, it's actually not because we are increasing the gas concentration of LVOC. And we also have SVOC, but we're not increasing that. There might be some conditioning there. So yeah, it's all based on our settings. So it doesn't have to be effective free.
Oh, I see. You didn't change the SVOC. Okay, that is.
Yeah, thanks for the amazing talk. I'm wondering, your growth factor of 3 clearly depends on the actual volatility of NVOC. So do you have a reason to believe that the SVOC is the part of the space because NVOC is some type ELVOC, so we can probably smaller growth factor because the operation will be.
Yes. So right now we are at a very preliminary stage. And as I've said, we are planning to refine our regime and yeah, thank you for the suggestion.
Thank you. Is it possible that you can explain the experimental results simply based on the fact that the bulk diffusion coefficient of the viscosity of the particle, where the viscosity is lower for the wet ammonium sulfate state, and then it's higher for the SOA, and so it's simply kinetics. What you're observing in the experimental results is simply the kinetics of partitioning, time scales for partitioning, and that you don't really need a condensed-phase chemistry scheme.
So I think for their experimental measurement, they found that when they grow wet ammonium sulfate and SOA the same, they start at the same diameter, they gave them the same gas phase products. They observed much higher yield when they are growing wet ammonium sulfate seed, and that's actually indicated in particle phase reaction, not other factors.
Correct, but I'm arguing that what you're seeing here is after giving the gas phase a certain amount of time to partition to the particle phase, that if you gave the SOA more time, it would eventually match the wet ammonium sulfate. That is the experimental result is simply a viscosity or a bulk diffusion coefficient artifact.
Yeah, their experiment is implied is slow too, that the particle goes out after 4 minutes. So
yeah, I'm sure one would argue that 4 minutes is short.
yeah.
Great, great. One more question.
Thank you for the talk. I just have one question. So for your mechanistic model, when you consider condensed phase reaction, does it include the reaction in the bulk, or does it also consider the reaction at the particle surfaces? Because chemical reactions can be accelerated at surfaces.
Yeah, that's a good question. So what I'm not showing here is another 2 line that shows the growth of dry ammonium sulfate, and we are not looking at that because we want to start with the simplest case. So for the wet ammonium sulfate, see the condensed phase reaction during the aqueous phase. And if it's growing a dry ammonium sulfate seed, then you would expect reactions on the surface.
Last speaker of this session is Nana Milis, an academic research fellow at the University of Helsinki. And she will talk about atmospheric salt particle formation and evolution.
Right, great, thanks. So, I'm English, and instead of some sort of information, I will only.
Okay. Okay, yeah, so I just want to make sure. It's
From condensate
somebody wanted to
we know that this kind of that particle formation is very important phenomenon in the atmosphere. And in this presentation, I will focus on acid and base molecules, but of course, like substance would be involved in this kind of studies. So we have a lot of water vapor in our atmosphere, and water vapor can participate to the cluster and particle formation. And water can either stabilize or destabilize cluster structures. And because of that, it makes it very difficult to estimate the role of water in particle formation. So some of the clusters may be stabilized, and some clusters may be destabilized because of the water vapor. So that's why it's difficult to say whether water in certain cases affects increase or decrease in particle formation. So why we are interested on water and other small molecules? So we know that molecules can collide to each others, and if the molecular interactions are favorable enough, they can form clusters. And clusters may grow to the aerosol particle size, and then aerosol particles can directly or indirectly affect our climate. So most of the people here are doing some larger scale simulations, and I'm doing some molecular level. So the difference in the diameters of Earth versus the water or other small molecules we are studying is roughly 10 to 17. And however, these molecules are still very important in the radiation balance of Earth. So first, we have this example case of the base monomer hydration. So we have ammonia, dimethylamine, trimethylamine oxide, and guanidine in our example case. And then we are studying that if we have under certain conditions, even here, we have the steady state concentration of the base, that how many water molecules are in these conditions have that base monomer. So the first line takes the 0, so it is the tri monomer, and after that it's decreased by 1 water molecule. So we can see that in the case of ammonia and dimethyl and guanidine, these monomers mainly exist in the atmosphere in their tri form. The trimethylamine oxide is a bit special case. So if we have trimethylamine oxide in the atmosphere, it is mainly in its hydrated form. And this is because this bond between nitrogen and oxygen has a sugar-aided character, so it is largely stabilized by water or any other interaction. So it seems that this base monomer hydration is increased when the basicity of the monomer is increased. So then we have some examples of particle hydration. So we have sulfuric acid with ammonia, dimethylamine, trimethylamine oxide, and guanidine. So it seems that the sulfuric acid-based particles, they exist in the atmosphere mainly in their hydrated forms. So in the case of sulfuric acid ammonia and sulfuric acid dimethylamine, you can see that we have slightly more hydrated clusters and tri-clusters. In the case of guanidine, we have mainly hydrated clusters. So have like 4 orders of magnitude higher concentration in their height. In the case of superconducting triangular oxide, then these clusters are mainly in their triangle. And again, it's because this triangular oxide is a big special case because of the trigger ion structure, but also because of the high. We can actually see that these particles seem to be more vibrated when the number of hyphen giving sites is increased. So then we have some examples of evaporation, like how the hydration affects to the evaporation rates of these acid-base clusters. So now we have an examples of sulfuric acid, methyl sulfuric acid, and nitric acid with guanine clusters. So I have calculated the effect of relative humidity, the evaporation rate using this kind of equation. So if this number is smaller than 1, then it means that the cluster is more stable in the presence of water. And when it is, and the number is higher than 1, then these clusters are destabilized because of the water. So it seems that depending on the site and composition of the cluster, water can either stabilize or destabilize the clusters. And that is the reason why it's very difficult to directly estimate the effect of hydration with the new particle formation rates. Because just seeing these values, it's impossible to say that whether the new particle formation rates are increased or decreased. However, we can model how water is affected to the new particle formation rates. So now we have the new particle formation rate here, and as a function of the acid monomer concentration. And we have again 3 different acid monomers. So sulfuric acid is green, methyl sulfuric acid is pink, and nitric acid is blue. These are then particle formation rates are simulated with these conditions. So we have some amount of quantity and low temperature. So in the case of sulfuric acid, there are 2 lines. So this solid line is the particle formation rate in dry conditions, and the dashed line is at high relative humidity, right? So we have solid line and dashed line, and because this dashed line is higher, it means that the particle formation rate is higher in the presence of water. In the case of these deep lines, the solid line is higher than the dashed lines, which means that in the case of sulfuric acid, the presence of water vapor is decreasing the particle formation. And then we have the nitric acid. So the solid line here is much lower than the dashed line. So it means that in the presence of water vapor, nitric acid volume particle formation is increased by roughly 4 orders of magnitude. So based on these, I have also calculated the hydration factors. With this simply just the particle formation rate in humid conditions divided by 5%. Particle formation rate are dry conditions. And from this table, we can see that these humidity factors are highly condition dependent. So different monomer concentrations, different temperatures, different relative humidities, these values are changing quite a lot. So it means that we cannot directly say that what kind of humidity factor is suitable for airline fusion. So we can conclude this talk by saying that these monomers, at least the base monomers, mainly exist in the atmosphere in their dry form, and the hydration seems to be dependent on the gas phase basically monomer. And the particles, they have some acid-based particles. They mainly exist in the atmosphere in their hydrated forms, and the hydration seems to be dependent on the number of hydrogen being sites. The effect of relative humidity to the particle formation rates may vary many orders of magnitude depending on the system and conditions. And that is mainly dependent on the stabilization or destabilization effect of these clusters. So how the water affects the stability of the smallest clusters. And as we saw, especially in the case of nitric acid, neglecting the effect of hydration in particle formation may introduce very high inaccuracies in large scale models. So that's why it would be very beneficial to have at some point some computationally cheap but accurate molecular level parameterization to compute this kind of hydration factors. So I want to thank you for listening to talk, and thank my group helping me, and I can answer any questions. Thank you.
Thank you. Any questions?
Very interesting. I wondered whether you had your predictions against measurements, for example, in the power chamber, because there they measured the humidity dependence of particle formation for many systems. And sometimes it was strong, and sometimes it was weak, and I don't think there was an explanation. So can you explain those results then?
Yes. So they have shown, so they're, if I remember correctly, most of those cloud experiments are made for ionic systems. So they have some amount of positive rays in their system. These correctly went wrong. These were neutral particle formation rates. But yes, we have compared some of the particle formation rates and see that there's those particle formation rates are pretty well with that cloud chamber experiments. We haven't directly compared these hydrated particle formation rates, but it would be really beneficial to do at some point.
Yeah, every experiment they do, I think, is neutral cosmic ray enhanced charge, so you should find it data.
Yes.
Any other question? Yes, thank you very much. We already running a bit, so we will come back after the coffee break, and thanks to all the presentations of this session.